Okay, we're back. So let's start with example 4 now. And it says to consider the following function. So this graph, sorry, I just put my hand in. That graph represents the distance traveled in minutes of a car. So it says find the average rate over the 2.5 hours. So from 0 minutes to 150 minutes, we want to find the average rate. So it says, we plug it in. This is AROC, of course. Then we'll get 30 minus 0 over 150, and that gives us 1/5. So our average rate over the 2.5 hours is 1/5. But now we're going to see how fast the car is going. So in miles per hour. How fast is the car going between 30 and 50 minutes? So if we look at our graph from 30 here to 50 here, it doesn't go anywhere. It stays at a horizontal line, which means that it is 0 miles a minute or that the car is stopped. So they stopped for a couple minutes, 20 minutes. All right, so when is the car traveling the fastest? So if we need to find out when it's traveling the fastest, we're going to look at the slope. So there are two sections of the graph that travel at the same rate of speed, and that's going to be the fastest it travels. And I'm sure that you've guessed that those two are between 0 and 30. So this first piece right here, and between 50 and 80. So from, where is it? Here to here. I don't know what's happening back there. Okay. And it says, when is the car traveling the slowest? So if we look back up here, we'll see that it's traveling the slowest between 100 and 150. And it says at 12 miles per hour. We don't know that yet, but we're about to. So between 100 and 150. So that's from here to here. Even though it's negative, the negative doesn't have anything to do with the speed. It does have something to do with the distance, but we'll talk about that as well in a second. So if we look at the slope, hold on, Campbell. If we look at the slope, listen, tell them hi. Tell the kids hi. Okay, so don't touch. So it says, how fast is the car going between 100 and 150 minutes? So we'll plug it in because we're going to use AROC on this one. So when we plug it in, we get 30 minus 40 over 50. Sorry. Over 50. Yeah, sorry. Okay, so we're going to get negative 10 over 50, which is negative 1/5. And the only reason it's negative is because our slope is negative. But that doesn't tell us anything about miles per hour. So if we have, she's singing. If we have 1 mile in 5 minutes, how many miles are we going to go in 60 minutes? So if we multiplied that by 60, we would get 12. Okay, and it says, part F says, why is the segment between 100 and 150 minutes negative? And since our Y values represent the distance traveled, that means that the car has turned around. So there's that. Don't touch this. And it says, what is the speed of the car at 20 minutes? So this we're going to use from 30 to 0, well, from 0 to 30. Because when we find these, if we want the speed at 20 minutes, it's a constant speed. If we look from 0 to 30, that's a constant speed. She's singing too. So 20 lies in that category from 0 to 30. No. So those are the intervals that we're going to use. So we have 20 minus 0 over 30. That gives us 2/3. It would be our answer. So 2 miles in 3 minutes. If we want to know the miles per hour, we multiply that by 60. And we get 40 miles per hour. So if you're wondering how we got these numbers, because there is no actual function, remember 30 and 0, those are the x values. So wherever 0 is, that's 0. Wherever 30 is, our y value is 20. So that's how we get these numbers. Okay, so we're going to do the same thing for part H. It says, what is the speed of the car at t equals 70 minutes? So for 70, if we look at our graph, here's 70. It's lying on this constant speed right here between 50 and 80. So we'll plug in 80 and 50. That gives us 40 minus 20 over 30. And then when we do that, we also get 2/3 again. Multiply by 60. Oops, I'm moving myself and not that purple thing. I can't make that move. Okay, so that's also 40 miles per hour because they had the same slope if we remember, if we've looked at that. And can you guys see behind that? I wonder if you can see behind that. My face. I don't know if you can or not. I can through the video, but I don't know. Okay. Example 5. Is this the last one? No, we've got another one after this. Okay. Example 5, it says when interpreting graphs, not all situations are linear functions. Let's think about this next scenario. So you've been waiting in line for 15 minutes to ride on the Orlando Eye. It took 10 minutes to ride to the top and 10 minutes to return to the landing level, which is near the ground level. So if we, here, you can have this. If we look at this graph, it took us 10 minutes to wait in line, or 15 minutes, I'm sorry, to wait in line. It took 10 minutes to ride to the top. So between 15 and 25, we're riding to the top. It took another 10 minutes from 15, I can't talk, from 25 to 35 to descend and come back down to ground level. And then we're back. So then we just are back on the ground. We're waiting. Okay, so that's what our graph would typically look like. And it says, think about how you would find the speed of your ride. It's difficult to calculate the rate of change of distance with respect to time at any given instant in time without having some measuring device when the function behavior is a curve. So example 6 says, we have also studied projectile motion. Suppose an object is projected from the top of a 112-foot building and its path is defined by the equation f of x equals 112 plus 96t minus 16t squared. So if we get a table in our calculator to graph this, it gives us directions. It says use the table above to find the average speed between 1.8 and 2.2. Remember to use the correct units and context to the problem. Okay. So we want to label our graph first. This is feet up on the y-axis. We're going to use AROC. So remember, AROC is that tangent or secant. It is secant. So see, there are 2 time intervals. Remember, AROC, there are 2, and that is secant. For tangent, that's when you only have 1 point on the graph. And that would be the instantaneous rate of change. So if we use the table, and we're using AROC, remember, between 1.8 and 2.2. There's AROC. Okay. So if we plug those in, so we're plugging in 2.2, that is 245.76. That's how we get this. Minus, at 1.8, it's 232.96 over 2.2 minus 1.8. Okay, so evaluating that, we get 12.8 over 0.4. And that gives us about 32 feet per second. So, that is the projected motion of that specific whatever we're looking at. Particle or something. I don't remember if it said anything. An object. Okay. So that's how you'd find that. We're just looking at speeds and stuff like that for this lesson. Sorry, they're pushing a toy. Alright, it says, suppose you wanted to find the speed at exactly t equals 2 seconds by using the slope formula and calculating the average change in a very small increments of x. We can estimate a rate that is close to the speed at a precise moment in time. Hit his head. Let's give it a try. Alright, so the graph at the right represents the table of values on the interval of 1.97 to 2.03. And that's for the function, are we given the function anywhere? I don't see it. Okay, so some function. And it says to find the rate of change in this window of values below, be sure to state the units. So if we do that, we're doing it from 1.97 to 2.03. So at 2.03, it's 240.95. That's how we get this first number. Our second number is 1.97. So at 1.97, it's 239.03. That's how we get this number. And then evaluating that, that becomes 1.92 over 0.06, which gives us 32 feet per second. So that's pretty simple. All we're doing is subtracting things. Excuse me, it says, is this the rate of change at the precise moment at t equals 2 seconds? When the line through the points 1.97 and then 239.03 and 2.03, 240.95 is drawn together, the straight line has now become an approximation of the curve. So if you remember from before, when we looked at secant lines, we would find the slope of that line. It's also what we did with tangent lines. And it says, the slope of the line shows the change in rate of the curve at t equals 2 seconds. The line appears to be tangent to the curve at 240. So these 2 points right here, that would give us a secant line if we were to draw those together. And then at 240, like right here, that is where that tangent line goes right through it. So if we were to find, it says, this is local linearity. In other words, if you choose any point on the curve and zoom in to an increasingly small interval of x, so numbers that are really, really, really close together, the graph will appear to be a straight line, or what could be assumed to be the tangent line of the curve at that point. So if we look back up at this, that straight line that we're looking at is actually this curve down here, but because we're so zoomed in to those really minuscule decimal points that are really, really close to 2, it looks like a straight line, and so we're able to find the instantaneous rate of change at a specific point. Okay. So it says, in summary, the rate of change of a linear function is given as the slope of its graph. If the graph is a curve, we can approximate the rate of change or slope at a single point P by choosing another point Q extremely close to P on the curve and then find the slope of the line between the 2 points. If you choose 2 points that are extremely close together, your approximation will be as close to the value of the slope as you need or want, and we'll call this the instantaneous rate of change at P or the derivative. So this is a very intro level of derivatives, because remember, if you think back to when we did them before, we did limits with them. We found derivatives using limits, and we also found derivatives with that power rule where you take the exponent down to the front, multiply it, subtract the exponent by 1. We'll do that some too, but for these application problems, it wants us to look at the instantaneous and average rate of changes again. So I hope you got something from this. Feel free to message me. I'll be posting the homework to go along with this. That's what I want you to work on for a few days next week, and I'll let you know when that's due. All right, guys. Talk to you later.